Robert Kalbank giving a talk after the reception at 5 p.m. today about the history of error correction through the lens of Reed-Muller codes. I also wanted to remind you, please sign up with Zulip if you want. So there you can submit the lightning talks or open problems for the Friday afternoon. You can also kind of organize social events. So it's kind of just a useful place to get organized. And yeah, that's the URL. All right. So we have Ted Yoder speaking about the recent results by IBM on QLDPC codes. So yeah, please take it away.
Yeah, thanks a lot, Nico, and thanks everyone. So yes, today I'm going to be talking about our paper from last August about new LDPC codes that we think are rather practical. So this is the archive version, and we hope to have a version 2 up soon, which actually sort of an unpleasant admission. There was a small bug in the numerics, but I think the results are not changed very much. But yeah, I will show the updated numerics in this talk, and you can soon see them in version 2 of the archive. Okay, so where does the story start here? I think everybody, well, we heard about the surface code earlier this morning. The surface code is this nice 2D local quantum error correcting code. And it's really amazing in that it has super high thresholds with just these local checks, and that you can also do a lot of logical operations with lattice surgery or magic state distillation. So these are really, you know, an exceptional example of really the exemplary example of 2D local quantum error correcting codes. But we also heard this morning, I think, from Louis, that there exists something called this Brobby-Poulin-Turhal bound, which says that when you have a stabilizer code that's constrained in 2 dimensions, like the surface code is, then its parameters n, k, and d, so the number of the block length n, the number of logical qubits k, and the code distance d, are constrained by this equation where n has to be greater than or equal to some constant times kd squared. So what does this mean for practical considerations? It means that when you actually go to implement an algorithm, you're going to have very large overheads coming from your error correcting code. So for instance, there's this paper by Gidney and Akara where they look at how to factor integers for RSA, and they end up using surface code blocks that are have distance 30. And this means that just to encode 1 logical qubit, you need roughly 2,000 physical qubits in your code block. And so this is before you even get into, you know, the magic states strategies, of which they tried several. Really, this overhead is, you know, coming from the nature of these 2D local codes. Right. So, and I want to point out that this isn't, you know, just because of the RSA algorithm for factoring. There are a bunch of algorithms that we might be interested in. Factoring is just one of them. Chemistry, dynamics. And so this paper by Michael Beverling goes through these algorithms and provides these resource estimates using, again, the surface code. And so if we look at, you know, for instance, superconducting qubits, which are the squares, and we look at error rates that we have now, which are roughly 10 to the minus 3, then we're looking at these filled in dark squares. And the resource estimates in physical qubits range from about 1 million qubits, you know, for the smallest algorithms, up to tens of millions of qubits, like for factoring. So to kind of put that in perspective, you know, what are sort of the machines we have today? Well, the machines we have today are like hundreds of qubits. So we're not even close to doing these algorithms. Oops, skip too far ahead. But even in 10 years, so if we look at, like, for instance, the IBM roadmap, then we plan like 100,000 qubit computer. And judging by those resource estimates on the previous slide, we're not going to be able to do useful algorithms with the surface code with even this 100,000 qubit machine which you can see, sort of schematically drawn here is sort of, supercomputer size, fits in a warehouse. So that's sort of discouraging. So really, we need to look for, if the resource estimates are like 1 million to 10 million qubits, and we're going to have 100,000 qubits, we really need to find like a factor of 10 or possibly more somewhere. And potentially we can do that with our error correcting codes. Okay, but to do that, we need to break this 2D local requirement. So it's a hardware challenge. You need to build connections that are not just local on the chip. Some examples of some examples of these couplers that are in development are the C coupler, M coupler, and L coupler, which we imagine connect. So the M and the L couplers, we imagine connecting different chips, both very close together with the M's, or at longer range between different fridges with the L's. But what I really want to focus on are the C couplers, which we envision are longer range connections that are on the same chip, between qubits on the same chip. Okay, so this can give us the power to implement some more exotic LDPC code. And yeah, so we can get away from the surface code. So here's a nice animation that my co-author Patrick put together. So these new chip capabilities sort of come in two related. Oh yeah, sorry. Go ahead.
Are you going to talk about how the fidelity or something changes as the connectivity increases in the C couplers?
I am not going to talk about that in this presentation. I think it's something that needs to be studied. Yeah. Right. So these hardware improvements sort of allow us to do a couple new things. First of all, you have to increase the degree of your qubits and also connect them at longer range. And this is actually tied to the second development, which is here, having biplanar architecture. And what this means, I'll get into a bit later, is that you can have couplers on essentially both sides of the chip, on the top and the bottom. And this also allows you to implement these longer range connectivity without crossing the wires. Right. So with these so we're going to sort of abstract away the hardware, right? And say, what can we do with if we allow ourselves these two layers of connectivity and longer range connections? So that's sort of our motivation. Can we now design LDPC codes that are practical for that hardware and also sort of small size? So we'll restrict ourselves to less than 1,000 qubits. And then we'll have a bunch of criteria we want to put on these error correcting codes. For instance, we definitely want low check weight. This restricts the degree of the qubits that we need. We want high encoding rates and distances to reduce the overhead of error correction. We want to be able to design circuits for these codes. And the circuits we design should give you low logical error rates and high pseudo thresholds in the circuit model. In the circuit noise model, I should say. And then, I discussed the biplanar Tanner graphs. And then we'd also like some way to access the logical information and read it out into potentially a processor unit. So I'll go through each of these points for the codes that we design. So it starts with designing the code. And sort of the general category that we'll look at are what are known as two-block CSS codes. So of course, these are CSS codes, like we heard about this morning, which means that there are both X and Z parity checks. The two-block part of the name, comes from the fact that you separate the qubits into left and right qubits. Okay, and the reason you do this is to make the commutation hx hz transpose equals 0 more easy to work with. Okay, so the x checks act on the left qubits via some matrix A that we will specify and instantiate, and they act on the right qubits by a matrix B. If we choose our z checks to sort of act complementary to that, so now B transpose on the left checks and A transpose on the right checks, then all we need to get this commutation of the x and z parity checks is that the matrices A and B commute. Okay, so you can work this out to simple calculation. And this makes it really easy to work with these codes as opposed to, just trying to choose random matrices hx and hz that somehow commute. So here on the right, I've drawn a Tanner graph, which we've also seen this morning. And these matrices A and B tell you how the different blocks of checks and qubits connect to one another. So a particular instance of two-block codes was studied by Lin and Priadko recently, where this is actually a more general family than what I'll present. So it includes ours. And what was really nice is that they could do an exhaustive enumeration of the codes, at least over the sizes they looked at. Okay, so what about our codes? So again, all we have to do is instantiate somehow these matrices A and B such that they commute. And the way we'll do that is by using these particular cyclic shift matrices. So the matrix SL is the cyclic shift of L items. And you can see some examples here. And we'll define variables X and Y, which are really matrices. So X is the cyclic shift of L items and its identity on the M items. And then Y is a identity on the L items and cyclic shift of M. So you can think of a grid, an L by M grid, and X will move you sort of left, and then X inverse will move you right. And I swapped left and right, didn't I? But that's okay. And then Y will move you up and down. Okay. And if you write A and B as polynomials in X and Y, then, these matrices clearly commute with one another. So we get exactly the property we want, that A and B as polynomials in X and Y commute. And so this is an instance of these generalized bicycle codes and also an instance of lifted product codes. So what actually some very nice codes that are probably familiar to a lot of you are contained in this bivariate bicycle class. So for instance, the toric code can be written using polynomials 1 plus y and 1 plus x. Okay. It's maybe not immediately obvious, but if you trust me on this, I think the one thing to note is that the total number of terms in A plus the total number of terms in B is going to be the weight of the parity checks. So at least the weight of the parity checks here matches what you expect for the toric code, which is 4. Okay, so then also you can get Haas qubit code, which admittedly is maybe not bivariate anymore because now there are 3 variables. 3 variables X, Y, and Z, and you can write these polynomials down A and B to give you this 3-dimensional code. Okay, so this is a large space to search over if you just allow A and B to be any polynomial. So we make some ansatz or what polynomials we will actually search over. So in our work, we'll choose A to be this particular combination of monomials, x, so a single x monomial and two y's. And then B will be a single y and two x's. Okay, so this, we started with a more general prescription and then sort of narrowed it down to something that found the codes that we knew existed from our initial searches. And now you can vary these integers AI and BI to find codes. So what do some of those codes look like? So here's a bunch of small instances, again, satisfying this less than 1,000 constraint, a less than 1,000 qubit constraint. The L and M are the orders of the X and Y variables. And then A and B are the polynomials, as defined on the previous slides. I'll focus in particular on this 144.12.12 code as an example in the talk. The thing I'm interested in, demonstrating on this slide is that if you look at this net encoding rate, which is the number of logical qubits divided by the total number of physical qubits, including the check qubits. So the number of check qubits we use is also equal to the size of the code. So for instance, the 144 qubit code has also 144 check qubits. So if you look at this net encoding rate, we get very large improvements over a surface code of the same distance. So for instance, the 144.12.12 compared with the distance D, 12 surface code, has roughly a factor of 12 improvement. Yes, and the last thing to note is, of course, all these codes have check weight 6 because the total number of terms in the polynomials A and B is 6. So here's again some nice Patrick animated slides showing the bivariate bicycle codes and a particular layout of these codes, which I think makes an interesting way to think about them. So we can place the qubits on the surface of this torus and also the checks on the surface of this torus. And you'll notice that the checks and qubits are connected to each other, to adjacent checks or qubits. And so if this is I'm drawing the Tanner graph here. So for instance, at this moment, this check has just weight 4 because it's connected to these 4 qubits. And this is actually a picture of the torque code, which we're familiar with. But the bivariate bicycle codes take this a step further and add longer range connections to these checks and qubits. So in particular, this is these are the connections, I believe, for the 144.12.12. And the range is determined by the exponents in those polynomials. So that is just one example of the longer range checks. But also these codes are translationally invariant. So if you want to figure out where the longer range checks are everywhere else, you just shift that example around. So that's what's being shown here. And if you prefer to see everything at once, the whole 288 qubits in one picture, then you can just cut the torus apart and lay it out in this rectangle as is standard. So where the right side is identified with the left side and the top with the bottom. Okay. And here the checks are squares and the code qubits are circles. And they're connected according to the Tanner graph. Okay. So having gone through the code construction, we found a family of codes with pretty low check weight, weight 6. And I think they also demonstrate very high encoding rates. and distances for small codes. So next, I'll talk about how to actually measure the syndromes, and that will lead directly into the estimates of logical error rate. Okay. So I think we heard from Yashka about hook errors and how those can be detrimental to your error correcting code. But let me just go through that quickly again. So for instance, you could have an X error occurring at some point in your circuit, and this will spread through C-naughts. Right? So if it happens on the control of a C-naught, then it will also spread to the target. And so the single X error, by the time it gets through the circuit entirely, will have spread to 3 X errors. And this means that one order P event, the single X error, actually turns into something that really should have been like an order P cubed event if all these errors had to occur independently in the channel noise model. So this makes circuit design kind of a challenge. So to tackle the challenge, really we just did a computer search over valid circuits for measuring the syndromes. Okay, so we ended up finding a depth 8 circuit for measuring the syndromes. So this is one cycle of the syndrome measurement circuit. Each C-naught here is a bundle of L times M C-naughts. So for instance, for the 144 qubit code, these are bundles of 72 C-naughts. And you have to be careful with the order of these C-naughts to make sure that the operators you're measuring actually are the correct stabilizers. But the C-naughts can always be associated with edges in this Tanner graph. So the Tanner graph tells you exactly the connectivity that you need to build in your physical hardware. Right, so you can use the same circuit for all of the bivariate bicycle codes. Some, if you want to get into the finer details, you can try to vary the circuit for a particular code, and that can actually do better in some cases. But for what I'll show, we use the same circuit design. And I said we searched over all of these. There are 936 different variants, and they just differ in this C-naught order. We try to select the circuits to maximize what's known as the circuit distance. So that's what I'll try to explain on this slide. So again, of course, hook errors are a problem. And this means that if we define the circuit level distance, dcirc, as the smallest number of faults that can create some logical error without triggering any syndromes, this means that this dcirc can actually be smaller than the code distance. If you actually do simulations of the circuit with this circuit noise, the logical error probability will be roughly the physical error probability P to the D circuit over 2. So, empirically, this is why we want D circuit to be as large as possible, and it's upper bounded by the code distance D. Okay, so I should display this earlier, but D circ is less than or equal to D in general, and for our circuits, D circ is actually less than D. We observe that D circuit is roughly, or it is D minus 2, at least as far as we can tell up to the 144 code. And we can estimate these circuit level distances by running our decoder on the circuit. So what is the decoder and circuit level noise model? So our noise model is rather standard in quantum error correction. It's the circuit-based depolarizing noise. So there's a variety of components in our quantum error correcting circuits. We can reset qubits to either 0 or plus. We can measure those qubits in Z or X basis. And we can do C-naughts or idle gates. Each of these could, in general, have their own separate error probability. For our noise, which is just the simplest case imaginable, we set all of these probabilities equal to p. Okay, and having done that, we can essentially construct the decoding matrix that's required by Yashka to run the BP and ordered statistics decoder. So that's what's done offline. We we inject every single fault into the circuit, propagate it through using Pauli-Clifford simulation to determine what syndrome that particular fault has. And so this we can assemble into that decoding matrix, and it's what we call the linearized noise model, because we just look at every single fault individually. So this gets put into our favorite decoder, which for us is actually just the Rafi implementation of BP plus OSD. And also what this decoder takes is a particular real syndrome, a syndrome instance from potentially multiple stages of the syndrome extraction circuit. Okay, so for our simulations, we use D rounds of syndrome cycles to feed into the decoder. And then, of course, the decoder spits out some correction, and we can compare that with the actual error that occurred and determine whether a logical error happened or not. Okay, so that's our Monte Carlo simulations, give us some idea of the performance of these bivariate bicycle codes. So we could simulate up to the 288 qubit code. It gets difficult to sample as your logical error rate goes down. I should say that this is the logical error rate per syndrome cycle. We get a logical error rate after those D cycles, but then we eventually divide by D to get an estimate of the logical error rate per cycle. At physical error rates that we consider reasonable are somewhere between 10 to the minus 3 and 10 to the minus 4. I think what's really interesting is the comparison of the bivariate bicycle code with the surface codes. Here I'm showing in the stars indicate surface codes from distances 9 through 15. And we can see that this LDPC code, this 144.12.12 code, is performing just about as well as we expect. So it's between the distance 11 and the distance 13 surface code. And that kind of makes sense because it's a distance 12 LDPC code, although our circuit distance is only 10. So you can explain this, sort of flattening out here at low logical error rates as due to the circuit distance being less than the code distance. Yes?
So these numbers assume that the comparison assumes that the local C0 gate is as good or bad as the long distance C0 gate.
Yes, that's right. All the C0s fail with probability P here.
Okay. And do you have an estimate of what that might actually realistically be? Like, is that going to be true? Or because I would assume that long range C0 gates are going to be.
Yeah, I would be surprised if it's true. But, I don't have any estimates from the hardware guys about that. Yes?
Are you using BPOSD for the surface code in that part as well?
No, I think this is minimally perfect matching, yeah. Any other questions? Okay. So, so now I think I discussed sort of the big thing that we care about, which is the logical error rates. I think the conclusion here is that you don't suffer too badly for introducing these higher degree checks. The logical error rates are where you'd expect. assuming we can build the gates well, which is an assumption. Yeah. So now I want to discuss, some architectural consideration, which is this biplanar Tanner graph. So the idea here is something called graph thickness. So I think this was maybe first discussed in the context of quantum error correction in this paper by Tremblay, Delphos, and Beverland. And the idea is that given a graph, G, which let's think of it as the Tanner graph, you can define the thickness of this graph as the minimum number of planar layers that you can partition the edges into, right? So for every edge, you say, this edge is going to live in layer 1 or 2 or 3, etc. And if each of those graphs, those edge-induced graphs, is planar, then that's some instance of a certain thickness embedding of the graph. So this thickness theta G is then the minimum over all those different planar embeddings. It can be shown that a degree D graph has thickness at most D over 2, or ceiling D over 2. So for instance, for our Tanner graphs, which are degree 6, the thickness is upper bounded by 3. But can we do better? So I'll hope to convince you with some Patrick drawn animations again that a thickness 2 embedding is possible. So here is the Tanner graph drawn on the torus as earlier. And if we just look at some subset of edges here, these cycles, then these are just wheels, sort of wheel graphs like this. And it's some collection of these. It's more than 3, but I've drawn 3. This graph is obviously planar. So we can just put that graph into layer number 1. To look at layer number 2, we have to look at the remaining edges. So the edges that we did not put into layer 1, that's something like this. And with some rearrangement or some redrawing of this picture, you can turn this into wheels that go around sort of the longer dimension of this torus. Okay, so that step's a little hand wavy, but I think if you stare at that picture enough, you can convince yourself that this is the same graph. And so again, these are wheels, which we can put into the second layer. Yes?
I thought that these would be layers that stack on each other so that vertices, a single vertex is
Yes.
stacked.
Yes, that is the case. Yes. Yes. So a planar graph is still planar regardless of where you position its vertices. This is, I have a reference. Yes.
Essentially routing all having a routing layer in the middle.
It can increase the length of the edges for sure. Yes. But because you can reposition the vertices and keep the graph planar, then you can always match up the second layer with the first layer.
So why is planarity so important if you're going to have these long winding?
Right. So you don't want the couplers to cross.
What about if you have to wind around in a
So I'm told that that's in principle possible. It may not be what you actually want to build. And we have some results on more practical layouts. But at least as, sort of abstract criteria for what you want your Tanner graph to look like, this thickness embedding, thickness P embedding is a decent criteria. Yeah.
Maybe a related question, I guess. Is there some metric of, say, like how close some of these connections need to come frequently with either other qubits or other couplers that you can formalize that would maybe embody this in a little bit more concrete?
Yeah. It's not something we looked at. But yeah, I agree that would be an interesting thing to study.
understand correctly that on this two-layer graph, there are actually local couplings, meaning you only go to nearest neighbor rings or nearest.
No, it's not like that. So the edges can be, these are just planar graphs. That's all I guarantee you. But the edges could potentially be long.
Has anyone at IBM like sat down for a day and like tried to draw out the like 144 qubit layout or anything like that, just to see what it looks like? Or
Yes, yeah.
crazy?
Yeah, it's a little crazy. I think if you restrict yourself to the strict thickness 2, it's even more crazy. But there are so the actual way that you get from one layer of the couplers to the other is through something called a through substrate via, or TSV. And you can actually use more of these if you want to transfer back and forth between the different layers, and therefore reduce the edge lengths that you need at the cost of potentially more TSVs. There's some optimization.
Yes.
Yeah.
Increase the close distance. Well, how does the longest long-range interaction scale?
So we just have some finite examples of codes, but you would have to, like, in order to achieve parameters that are better than the surface code, you will have to increase the length of the connections with the size of the code. That's necessary.
So to suppress error, you need a virtually long range.
Yes. Well, not necessarily to suppress error, but just to beat the Bravi-Poulan-Turhal bound in terms of code rate and distance. Yeah. Okay, so that's biplanar tanagraph, and I have just a few minutes for this last slide about how we envision doing logical gates, or like using this as a logical memory where we can read information in and out. So there's actually two parts to this story. So the first part are called automorphism gates, which are essentially permutations. The light's coming back on. Permutations that preserve the stabilizers of the code. So essentially, you can permute the qubits by some permutation pi. And if you can undo that permutation by also relabeling your stabilizers, then we call this an automorphism. So although it preserves the stabilizer group, so it preserves the code space, it can change your logical state. So it can change the basis of that, the logical basis of that code state. So for the bivariate bicycle codes, what do these automorphisms look like? Well, they're maybe what you would expect. You can shift qubits to the right and left, and up and down. Just translations. And this actually feeds into the to part 2 of this story, which is that you can actually build ancilla systems to read out certain logical operators of your code. So here we imagine that we have our bivariate bicycle code. It has some abstract Tanner graph drawn right here. And then we attach these ancilla systems for Z and X to the qubits of this bivariate bicycle code in a particular location. So it can measure out a single logical Z and a single logical X. Now there's more than a single qubit in this bivariate bicycle code. So in order to access all the qubits, you use these automorphism gates to shift the qubit that you're interested in measuring into the correct location in the code. I guess the other thing I should mention is not only can you measure the logical X and logical Z, but you can also teleport out one of your qubits into a surface code using these ancilla systems. So this is a really neat like general construction, which was presented in this paper by Cohen et al. Okay, so with that, let me conclude. So what I hope to convince you of is that there are practical LDPC codes on less than 1,000 qubits. They have a bunch of nice properties which make them competitive with the surface code and hopefully implementable on superconducting hardware or others. I think that these codes and their performance are generally encouraging for using codes that are beyond the surface code. So yeah, again, you can check out the paper, which will be updated soon, and you can also contact me for more info. Thank you. Yes.
How do you implement the permutation?
That's a good question. I have a slide for it. So you can do this. This is a depth 4 permutation circuit that shifts you 1 lattice spacing. And so essentially the idea is that you have these ancillary qubits lying around, which you can initialize in 0 and then do these 2 C0 swaps with your data qubit. And if you do that twice, then you shift 1 lattice spacing while being fault tolerant. So you don't introduce any like 2 qubit errors on the data. You're always swapping a data with an ancilla.
I think about some this code considered here.
Yes, I think that would be nice to do. We don't have any idea of how the code parameters scale in the asymptotic regime. Yeah, I mean, it's definitely something I think that's worth thinking about.
Any more questions? Actually, I have a question. So,
Yes.
So you found these nice examples. Do you have any feeling of whether they belong to maybe like a larger family or?
I think that's similar to that question. Yeah. I mean, obviously we can, pick out some class of polynomials and say that these are the codes that they make. But so it is part of a larger family in that sense. But I guess the question is that family interesting outside of this finite regime? So I haven't. I mean, we don't have any results, bounding the code parameters at larger sizes. But I think that is definitely interesting to do.
Well, if I may, it's a question and a comment at the same.
Okay.
So the Bravais-Terhal bound, which you put this constant C.
Yeah.
In fact, sort of, if you move it to the right-hand side or left-hand side in your notations, it will be the size, the area of the stabilizer generator. So for the toric code, it's basically 1 because it's 1 local measurements. In your case, it is bigger. So if you follow their arguments, you can get it. It's basically, they just didn't care.
Yes, that's definitely true. If you fix the range of connections that you're allowed, then of course you can change the constant in the Bravais pool.
So the comment is, the answer is this, basically, this is what you expect for this kind of codes. But the question is how far you are from that bound. So you increased K from 2 to, let's say, 12 and the distance that you increased, I think it's around 10 meter size.
The range of the coupler, yeah. So I think, yes, I mean, definitely in order to get interesting asymptotics that are better than Bravais pool and Terhal bound, you need to allow your connections to grow with the code size. Yes.
Okay. Any other questions?
Just as a comment, maybe.
Yes.
They seem to be connected to specially coupled LDPC.
Oh, I am not sure. Okay.
Maybe. Prerogative here, maybe.
Yes, I think there's.
So, I mean, when you think about local interactions, I mean, use your toric code as an example. And that is an example where you have sort of 2-dimensional locality. when you pick out those polynomials, that's also naturally two-dimensional. I don't know whether I'm adding.
Spatially coupled, I guess, like they have
Spatially coupled, yeah.
yes, long-range connections, right? Like so between LDPC layers, like long-range connections.
Well, I actually like to think of two-dimensional spatially coupled as being shorter range. However, you're right, because you can, in the classical world, you can think about windowed decoders that only look at a subset of the qubits. They progress along the qubit. Of course, there are different error probabilities, so that makes them more practical in one regime less practical.
Since everybody's just commenting.
Go for it.
Just reiterating, I mean, you just touched on it, and Shruti also asked a very pertinent question. And I think there's a lot of theorists in here, and a few experimentalists as well. So you can. I don't think there's any systematic study, and somebody correct me if I'm wrong, that understands the error rate as a function of the distance for these types of gates. And for us to really think confidently about this as an abstraction, we need to understand what a good function looks like for that. Because ultimately the error rates do have to be sufficiently low. And so I know like in superconducting qubits, for example, as long as you're doing gates in the near field regime, okay, maybe it's fine to have long-ish range couplings, but not so far that you leave that near field. Because now it doesn't really make sense to couple beyond that. So, and in other architectures, maybe it's different. But I think without a clear ansatz for how to define gate fidelities as a function of that distance, it's a little premature to ask these questions theoretically about like, oh, how does it scale, this, that, and the other. Now that said, I don't think any experimentalists have done from an experimental perspective, boring task of trying to map this parameter space out. There's more exciting things that they could be doing. But it would be an important thing for them to do, and I would love to see the results of such a study. So, any comment? Thank you, Tim.
Yes, I'm looking forward to those experimental results as well.
All right, let's thank Ted again.